Privileged to be a part of this workshop today. Briefing content, I'm going to go over the various tools we use with the CST tools and show a little bit about our analysis process, how we can evaluate vehicle shielding, do some detailed models of different joints and seams, and model wire harnesses to make a good system model, and then conclude with more on the focus of this workshop with the lightning analysis and verification that needs to be done with various models. So with an overall analysis process that is supported by the CST tools, you're able to use the multi-team geometry, CAD modeling inputs into your simulations and assign materials and have a representation of the geometry and the materials in your model. You can apply your analytical mesh, which is very important because if something is not meshed properly, it is invisible to the model. It is not really represented in the model. And you are able to solve with the time domain simulation tools the band-limited impulse response, look at the Fourier transform, and actually convolve with specific threats such as lightning, and do various data reductions and calculate fields and pin voltages and such that are important to your system. So these tools are very helpful to analyze and support trade studies. When you are working with a team, you can't wait to build the first vehicle to find out if you're okay. You need to be making decisions along the way with the team and defending various features that are important to EMI, EMC, and lightning. So moving into vehicle shielding, when you look at a vehicle, in this instance it's a ground vehicle, and ground vehicles get struck by lightning as well. You have a cavity and various subcavities within the vehicle, and there's a point at low frequency, as depicted on the right, that you get good shielding. Apertures really do not become electrically significant until you get up to a certain frequencies, depending on the size of those apertures and seams. Eventually, you enter a part of the response of the structure to where it is overmoded and you get very complicated reflections, multiple reflections in the cavity, and things look rather statistical. You don't have to move very far in a cavity before you're moving from a maximum to a minimum, and so it's very complex after you reach the higher frequencies of that cavity, depending on the size. So platform shielding is very important at resonance, where the energy capture of the system is greater, and you have higher surface currents driving joints and seams and wire harnesses. And so you do get the roll-off, and so all these things in a model need to be looked at. And with lightning, you can maybe not look at the higher, you don't have to look at the higher frequency, slightest seams and apertures. You're mostly looking at apertures and seams that are conducting lower frequency currents. So in the end of all, the point I want to also make is that when you're making a system model, you have to put in the things that are important to your model, but don't keep all this extra detail that looks good. When you manipulate the CAD, you say, wow, that's a pretty model, or that looks, precise. Well, you can, if you don't represent various things properly, you can be precisely wrong in your model. Okay, so moving on, shielding, everyone knows about the concept of shielding, but one thing that's often overlooked is that shielding is both a function of frequency and time. When you conduct shielding measurements, you are often using continuous wave probes that have a high dynamic range, but you have to have a settling time, and it has to, you are actually looking at the long-term response of effectively long time dwelling sine wave at a certain frequency. And so what happens though when up to that point where there's a lot of transients is energy is moving in the cavity and being distributed by wire harnesses, and it depends on the pulse width and duty cycle of your transient energy that can make a difference, and you can actually have lower shielding up until the point that you reach a maximum cavity response, and then it can actually then settle to the CW response. So sometimes you can be fooled, and you need to look at the what is important to your problem and the kind of transient that you're dealing with. So it does take time to develop shielding, and it takes time before a shielding minimum can actually develop in a cavity. All right, and then when you look at transient responses, in this example, the lower amplitude sine wave there, about the 0 voltage level, is representing the coupling that you would get with a CW response. Let's say in a wire harness, 50 volts per meter, your standard box level qualification levels. And that is maybe what you would get there, but then the larger pulsed transient energy that's shown there, that's going over 30 odd volts in the interface, that energy represents maybe what you're getting with a pulsed radar or some transient field. Well, what's important is you got to at least protect for damage. So getting up around 30-some volts in an interface could be a potential problem with different devices, depending on what they are. And then another thing to consider is that what you may be able to handle with the feedback control loop that's in your system, you may be able to handle a brief disruption and have upset for a limited period of time. And so your software and how your system is architected can help you deal with these transients. In the case of lightning, transients can be very persistent, and you would need to probably introduce shielding in the interface, differential balance type of circuits, so that you can get the coupling down below a common mode rejection level for a particular device, such as EIA 485, you get your plus or minus 7 volts. So I have noted on this figure various things of interest, like the plus or minus 7 volt mode threshold that exists in most serial data interfaces. And so I wanted to make that point that data protocols are very important to how you can handle your upset periods. Now, going into building a system model, you need to account for various features. And you look at an individual slot. Well, as you're trying to build models, it's important that you look at these smaller features and don't start building the big model right from the onset, but actually try to understand how you use the tools and say, well, here's an example in IEEE paper, and here's a particular cavity, here's a slot with certain features, and let me see if I can analyze that. Let me get that conquered first. Let me understand that I'm using the tools properly and developing effective models for something that is already well solved, simulated, and perhaps even tested, as is this case in this example. So it's important to master the simple before you move on to building your complex model. So you can take these bits and pieces, different seams, different joints and apertures, and then be comfortable to develop your overall system model. And then I will only touch on this briefly, but in reference 7, I expanded on this in an IEEE conference where you can actually measure, actually model detailed joints, fasteners, spacings of fasteners, paint systems, and actually finding out what the shielding property is for various seams. And these types of seams, riveted structures, are very common in the aerospace defense product lines. So the other thing is, with lightning, you have an added complexity, which was mentioned very, very effectively in the previous presentation, that these fasteners not only are touching a homogeneous sheet of material, but there's non-homogeneous directive fibers that are touching fasteners, and fasteners become a kind of a bus bar for all these fibers, and it can be very complicated. But nonetheless, these fasteners, if you're not just looking at the lightning energy trying to burn through various layers and the resins to get to these fibers, it can just do that at the next fastener that is tying the skin to the substructure. And that those fasteners, someone could take this approach, this modeling approach, and actually expand upon it and look at different graphite layers touching fasteners and looking at the joint properties. So I will point you to that reference, and I'd like to see some work that someone could do to expand how you can model fastener joints with these composite materials. Also, people have often used copper tape to enhance shielding in a certain region, and well, you wonder, well, how do I know how effective that copper tape would be? Well, this model was done just to show that you can take the analysis tools, looking at the connectivity of the adhesive and the copper tape, the thickness of the copper tape, and build an effective model to find out what kind of shielding you will get with the use of copper tape. So in this model, I have worked with CST, and there's various techniques you can use, and one is to have sort of an observation box that you can make a little chamber to test the front face, which is the green face, was actually the area of interest. And by having the red box that is assigned a free space property, the energy that comes in through that green face with the antenna you see on the left, lower left, that horizontal polarization is depicted for this example. And so you're driving currents around through those seams, and this observation box, this free space box that you're putting on the back side, is just to make sure that you can see what's happening at the face without causing other artifacts in the analysis, such as cavity resonances. So the energy that would then be relaunched on the inside of that observation box, once it reaches one of the walls, would tend to just disperse as if it's going into a free space medium. And that keeps energy from coming in from the side and just forces it to come right through the front face, and also make sure that your analysis results are not affected by cavity resonances, so you can focus in on a particular seam. And so using that technique, I've achieved results showing, because that was a square aperture, a square seam, when you drive it horizontally or vertically polarized, you get the same coupling, roughly the same coupling. And so because, and if it was not that case, if it was more rectangular, or one vertical dimension of the seam was a longer extent than the horizontal, whatever polarization you have that drives across that seam is the one that's going to create the greatest coupling. And that's all stated here. So I'm going to move a little more quickly to get into the lightning that most are interested in today. Also, you can also take the tools and, using compact models, develop very efficient representation of screens. And in this example, I had more of a louver, an air vent into a bay of a system. And you can see in this result that just with the louver where the air can move in, that I get a certain profile of shielding effectiveness in dB versus frequency. And then you see with that the shielding's not very good, the green line with the louver only. And then you see the green, the line with the screen only, and then the combination of the two. So these tools, once you tune up these subsystem models, then you're ready to go into a full system model with confidence and have the proper representation of these features where your energy can come in. Wire harness shielding is very important. That is, we are, when we're looking at coupling, we of course care about direct effects with lightning, but from a system, electronic system, we're concerned mostly with the electronic system not being upset or damaged by lightning or other EMI environments. So wire harnesses representation is very critical in a model, and CST is very helpful in capturing these types of details and helping the analyst develop an effective model. And the one thing to remember, and the way that the CST tools can address this, and is to not only consider the wire harness as a victim, where it's soaking energy and that energy is coming into that and affecting the wires, but actually wire harnesses, especially with lightning, you have relatively high conductivity represented in the shields of those bundles, and that low frequency energy of lightning will be attracted to those shields. And even in higher frequency phenomena, and especially resonant frequencies, the wire harnesses are not just victims, but they actually are involved with the distribution of energy within a cavity and conducting energy from one bay to another. So the tools currently are able to use a wire cage approach with little cross ties, little circumferential type of connectors that tie and bus all of these 5-wire conductors together, and you can have 2 LRUs, line replaceable units, that are connected by this harness, and you're able to make predictions as to what the current is on the shield and what the current it would be in the center pin, in the analogy of it being a coax, looking at the common mode coupling through that shield. So this is fully coded in the tools, and you're able to take, as we're all familiar with, looking at the transfer impedance of the shield, looking at the joint resistances, even at connectors, can be represented in the model, the intrinsic braid resistance, the mutual inductance term that's involved with the apertures and seams of the optical coverage of the cable braid, and then calculating all those as a per unit length and adding that into the model, you're able to get a full representation of your shields. And the results of that, we are finding, where you can look at as a function of frequency or even a specific transient response, you can look at the current on the outer end, the bulk currents, and there's 5 of them shown on the top curves, a set of curves, and you're seeing that there's pretty good even distribution with this wire cage method. It's been very effective. And then you can see, as a result of that shield, how you're able to get very good low-frequency shielding. And then as you get, depending on the type of shield you have, if you have something with a low resistance term for the transfer impedance, you're going to get very good shielding. And then as you get into higher frequencies, the braid apertures are going to start lighting up and creating a flow of energy into the system, so the shielding is not as great, represented for the prediction of the internal current. And this is also now, the tools allow you to change the first universal solve is with the cable, the center conductors, termination resistances, impedances being that that's the Z0 of the cable, the virtual coax. And then you're able in another post-process to change those resistances to, something other than Z0 and actually look at the coupling. And then another interesting thing, where you don't shield, you can look at with the tools when you have an unshielded stub, something going out to something that doesn't really promote a shield topology, or maybe in an aircraft you can't afford the weight associated with maintaining the shield in all of the bays. Well, you can look at the unshielded portion of the cable, and with this analysis technique that I'm showing here, I thought, well, if everyone's concerned about conducted emissions, and those are defined in various standards, for example, Mil Standard 461, what we use here in the U.S. For some aerospace systems, you say, well, if that's good and you actually qualify a piece of equipment that it cannot emit more than that, well, let me try to do an analysis using the listen represented in that. And so you're able with the CST tools to put in a circuit at that plate, to where you're going to have an unshielded, that's the interface where the unshielded portion of the cable is then going to be tied to a shielded portion on the left of that red little plate. So you're able to represent that, and the results show that, as you would expect, that with longer exposed wire without it being shielded, that causes the resonance with a 0.8 meter length unshielded portion. You see with the highlighted, the 88 odd megahertz for the resonant frequency there, and then what the coupling level in 349 millivolts for a 1 volt per meter excitation. And you can then scale that to your particular threat and actually have meaningful calculations to know how to size any filter pins and so forth, or even some transient suppression that you may need in the case of lightning. Okay, time is running a little long. I'm going to try to hurry. So now, some of you are saying, finally, guys talking about lightning. But so a lightning analysis, you have high voltage air ionization, voltage breakdown, and you get into these nonlinear effects. Well, this approach that I'm going to show you with the indirect coupling effects, the tools, I'm staying in a linear analysis realm. And now there's ways maybe to slice, actually apply a transient, look at your conductivity as a function of time, and readdressing the model for those time steps, and actually be able to do a nonlinear analysis with special care. But in this case, I'm going to talk about a linear analysis where you're not looking at breakdown in wire harnesses, or if you do have localized breakdown in a skin, you have an overall conductivity that is quasi-linear, that really isn't is staying where you can do a linear analysis. So you can create an effective current source, and a very stiff source, 1 megavolt, 1 mega ohm. There's actually now in the TLM tool, a current source that you can actually just set up from the onset without having to worry about all of this. And you can basically drive through your model and your different, the reactance of the channel and everything, and you actually get to deliver a current, a calibrated current at the vehicle and vehicle interfaces. And, this is a real world consideration because with lightning coming from a cloud ceiling and coming all the way, developing from the cloud to the ground, or hitting a vehicle flying and then exiting the trailing edge to create a channel down to the ground. After all of that potential energy and all that work that was done to create the channel, lightning current's not going to say, well, you're a tree, I'm not going to give you as much current. That current is an effective current source, and it drives roughly the same current through a tree that's not very conductive as it would a radio tower or a transmitting tower. So there's the same action integral but different energy dissipation depending on the resistance, as I show in that formula. And then other details, you know, when you start working with lightning channels, you got to model them effectively, as I'm going to show, and you need to make sure that you it's a current source. Yes, there's an E field, but you don't want, then in the propagation of that energy, you don't want it to be dominated. You want, of course, there's a linkage in Maxwell's equations between time varying electric fields and magnetic fields, but there's particular care that you need to make in creating the proper wave impedance when you try to look at indirect coupling from lightning. So most people, when they look at lightning effects, will say, well, if you're an aluminum structure or something with non-magnetic materials, that for the most part the energy will go right through there, go through that structure, especially if it's particularly thin. And the rate of change of magnetic field, at least the low frequency components of the magnetic field will, and the rate of change of the magnetic field will come through that structure. And then you have a loop area of your conductors that will then, there'll be a d-phi-dt type of coupling, and then the current will be the integral of 1 over L of that voltage that's created in that loop. So 10-meter away lightning, we have different criteria. So in a ground vehicle, in different systems, you may not, the probability of you getting struck may not be as great as an aircraft that's, flying around near the clouds and actually triggering lightning to a great extent. But if you're a ground system, you often can say, well, it's more probable for me to be near lightning and then to be directly struck by lightning. So the architects of these different systems, these ground systems, will actually require you to be 100% operational being a certain distance, let's say 10 meters away from the lightning channel. So this type of getting the wave impedance right is particularly important when looking at these nearby strikes where you didn't get struck directly. So you can use the codes and tools, and you need to make sure that you have the thin film representation of the structure so you allow the diffusion to occur. And if you just assume it's perfect, or if you don't properly assign material in the model, it will assume that you did not have diffusion as a interest in your model and will ignore that effect. So anyway, getting to like a NATO power connector where you have a vehicle that needs to have its batteries are weak or whatever, and you need to use another vehicle with a NATO power cable to start the vehicle or charge its batteries. And so this is illustrated in this example, and you have a ground plane that's represented there. And this model, you have two vehicles that are just notionally represented. When you give a presentation like this in an open forum, sometimes it's more difficult to show particular features of any system. So I'm just making a very simple representation and trying to see what's happening with the cable interface. And so what's important to the example of getting the modeling correct is over on the left-hand side, I have a lightning channel that is showing an indirect attachment 10 meters away from one of those, from the center actually of the cable. I wanted to see what was happening with that cable interface. And so I have the 1 megavolt, 1 megohm source, and then I'm actually putting a little shielded box where I have my source so that I suppress the E fields from this current flowing in that source resistance and launching a particularly high electric field. I want for this simulation to develop the wave impedances from a current source, from the current flowing in the channel and the magnetic fields that surround that channel of current. And so this problem is described here. So what I did for further explanation of this model, so two vehicles are connected together through the NATO jumper cable, if you will. 20 feet of cabling, 2-aught conductors. So we have represented this model, and I'll get to the results in the interest of time. So you're able to, from this model, by having an effective way to model the indirect lightning and controlling your wave impedances, actually looking at the current that is flowing in with the mil standard 464 lightning 200,000 amp lightning current, you are able to see in the lower left corner that's the threat, and on the right-hand side, you're actually seeing how that threat is coupling into the cable. And these NATO connector cables do not have shields on them, so this is the energy that's coming in, and because the cable is 20 feet in length, there are some rate of change current and magnetic field components that actually can excite resonances in that cable. And even though the energy is rolling off significantly at higher frequency, there's still enough high frequency content in a double exponential waveform to excite particular resonances in that cable. And then for the wave impedance predictions, just to show what went on in the model, by having this little shield around the local source in the model, I was able to control the wave impedance, and actually showing in the right-hand side how that the wave impedance of 76 ohms for fields close to that, 10 meters away. And then eventually, when you get far enough away, eventually the E and H fields will balance out in a plane wave. But in lightning, with a low frequency and the size of the channel, it takes considerable distances before you actually achieve the, actually it's 149 ohms of wave impedance at 10 meters and 76 ohms local to the source. So that's showing how effective that this local shield was in suppressing the electric field. I'm not showing that in this graph, but if you did not have that shield, local shield, you will actually get E will be dominating and be higher than the H field to an extent to where it'll be hundreds of ohms, much higher than free space. Okay, and one other thing, when you try to get the diffusion characteristics correct in your modeling, you need to make a simple model first. Don't just, okay, first time I'm using and trying to represent diffusion in my model, so I'm just going to take this big structure and I'm going to just go ahead and make my model with this big structure. Well, I would recommend that you would take and look at a smaller model and kind of get your feel around that model with an equivalent approximation circuit and actually see, is my model behaving properly? Do I know how to use these tools properly to get this required effect captured in my model? So I recommend that you take something as similar, like a diffusion cylinder problem, where you take a cylinder with graphite, and you could debate what is the conductivity of graphite in that direction. Well, you need to probably tweak that, and your ply layups, and you can assign an effective conductivity. And then you look at your length of your structure, your diameter of your wire harness. In this case, it's just RG218 coax that's in the middle, spanning between those two bulkheads, the red bulkheads. And so this is just there's actually a solid skin that's over here. This is just a wire representation of the structure so that you can see inside and see the cable. So approximate circuit is you have a current source represented in this schematic, and that is driving over into these first, the RJ, that's the joint resistances. And I have in the back, at the end of this presentation, a glossary of terms showing you what these different resistance and inductance values are and how they can be tuned to represent structure. And so you have that joint resistance where you first are tying that bulkhead to that skin, and you have the RJ, and then RS is the skin resistance. And then on the right-hand side, in that parallel with the skin, you may have some coatings. Maybe you did some mitigation for lightning, and you had some conductive layup or astrostrike or some other material or paint systems with some connectivity. So that you have your wire harness bonding, RBH, and then you're going through a wire harness path, or this could be a tube, a fuel line, or something like that, and you have the resistance of that harness or that tube that's inside that structure and the inductance of that tube. And then then you can project from that, knowing the current through a shield, you can actually predict the open circuit voltage given the resistance per meter and inductance per meter for the braid and the transfer impedance parameters. So the results of this, you can see the diffusion occurring in this. This is a circuit model, not microstripes yet, but this has been validated and tuning microstripes models to have the TLM solver and CST tools, having that actually predict this same behavior. And so with a TLM model, I'm actually able to get the diffusion very similar to the circuit model, to where I understand that I am modeling this correctly. And you can see the applied lightning and then the coax cable current. So you have to take, that's the current in one of the cage members, and you got to multiply that by 5. So, and then the circuit model. So by this, I'm saying, well, I'm getting good behavior in my model. This is working properly, and I can then feel confident to go ahead and use that modeling approach to develop a more complicated system model. So from that, you can also go further and look at the transfer impedance of that cable and that RG218 and actually look at the pin voltage and verify that with the TLM method that I'm getting close to the circuit approximation method and feel confident that I have everything in that model properly represented, and now I can move on to a more complicated system model. So that is the end of my presentation. I do have here abbreviations, references. I've tried to capture all the acronyms that I've used. Also some references here. Reference 7 there is from a IEEE paper where I went into the joints, looking at fastened joints, and then hopefully these things will be helpful to anyone that would look at this after I'm done presenting. And then also the lightning model parameters, trying to describe with the circuit approximation how you can derive and properly create a circuit term in a low frequency SPICE type of analysis, and actually look at representing your structure to tune up your models and your modeling techniques. That is all that I have. Thank you.
Thank you very much, Carl. Any questions here from the audience? People are getting already a bit tired here, Carl.
Yes, and I think I went over a little bit. I apologize. I had a rough start to my presentation with all the reverb.
Yeah, it has nothing to do with your presentation. It's just afternoon here, and we have seen a couple of presentations today. So thanks a lot. It was very interesting, and thanks a lot again for your contribution.